Right, so let's get started. So in this lecture note, we will derive the Gram-Schmidt process. But to derive the Gram-Schmidt process, we already discussed this procedure already. So let's briefly review the Gram-Schmidt process. So Gram-Schmidt process based on this one. 그죠? The goal of the Gram-Schmidt process was to produce the orthogonal or orthonormal basis for the non-zero subspace of Rn space. So what was the orthogonal basis? We have to discuss this one, 그렇죠? So for the basis one, linear independent and the set of the vectors should be linear independent and span double space. To be the orthogonal, so we require one more, I'll say, constraint, which was that orthogonal each other, 그렇죠? Within the vector, among the vectors. The orthonormal means each vector should be normalized to the one, 그렇죠? Now what the orthogonal basis? How can you do that? So given a vector x1 and x2, for example, let's consider the w. First of all, x1 and x2 are linearly independent, so it's going to be the basis for this W subspace, 그렇죠? So the question how to make orthogonal basis V1 and V2. So how can you do that? First of all, we just let V1 is at x1, then find out component of the x2, orthogonal to x1. So V2 is going to be x2 minus orthogonal fraction of the x2 onto the W. 그렇죠? In this case, W1, 그렇죠? W1 is going to be the line defined by V1 or X1. So it's going to be this one, 그렇죠? V2. So by using this, V1 and V2 are also on each other, and V1 and V2 span the space by X1, X2. So V1 and V2 is going to be the orthogonal basis. What about this? We have three vectors. So x1, x2, x3 are independent. Thus, this is the base for the subspace W of our four space. So, but in this problem, we have one more, assumption. This is a three-dimensional subspace. So, based on the basis property, in this case, x1, x2, x3. I mean the three kinds of vector that are independent. It's going to be the basis for the double subspace. In this case, orthogonal basis for the double subspace. So we can do similar things. The first one is that in step 1, let V1 is equal to x1. So which means W1 is equal to span of the x1 is equal to the span of the V1. So in step 2, let V2 be the vector produced by subtracting the x2. 그렇죠? x2. I mean the outside this substrate W1 is projection onto W1. So that is like V1 is equal to x2 minus also a projection of the x2 onto the W1. W1 defined like the V1, so it's going to be looks like this. 그렇죠? Based on definition of the orthogonal projection of the x1 onto the W1. So V2 is orthogonal component of the x2 orthogonal to x1, so V1, V2 is the orthogonal basis for the subspace W2 spanned by x1, x2. So, but here is one more step. I mean, this is optional step to clarify and to simplify the computation. We can just scale V2 to the V2 prime, 그렇죠? To simplify later computation. But this is just optional. If you can do, just use the V2. But we are going to use V2 prime. So anyway, the V3 is going to the vector produced by subtracting from the x3 its projection onto the subspace W2. W2. 그렇죠? W2. Determined by V1 and V2 prime. 그렇죠? So how can you do that? First of all, for some operation of x2, x3 onto the W2 spanned by 그렇죠? Spanned by V1 and V2 prime. So it's going to be looks like this, 그렇죠? Based on orthogonal complement theorem. Let's just use that. Then V3 is going to be the component of x3 orthogonal to W2. It's going to be like this, 그렇죠? Blah blah blah. So anyway, we finally found the V1, V2 prime, V3, which is going to be orthogonal basis, 그쵸? For W spanned by x1 to 3, initial x1 to 3, vector 1 to 3. This is orthogonal basis. That's the definitely Grant-Swiss process. Today we'll talk about this. 자, this is Grant-Swiss process. 자, before that, observe that V3 is in W because X3 and also operation of X3 onto the W2 are both linear combination of the X1 to 3, which expand W. So V3 is in W space. And V1, V2 prime, V3 is orthogonal set of the non-zero vector in W. Hence, they are linear independent set. 그죠? Linear independent set. Note that W is a three-dimensional space. 그죠? Three-dimensional space. Like this. 그죠? Like this. Three-dimensional space. Since it is spanned by linear independent set 1, x1 to 3. 그죠? So, anyway, by the basis theorem, V1 to prime 3 is the orthogonal basis for the W space. 그죠? They are also each other and they are linear independent set and span W space, so they are orthogonal basis. That's it. Orthogonal basis. So this is a Graham-Schmidt process. So from now on, let's formulate this Graham-Schmidt process. So this is a lecture theorem 11 in your textbook. 자, given a basis x1, 2, 3, and xp for non-zero subspace W in Orange space. So first of all, this is just a basis, not a orthogonal basis. 그렇죠? So the goal of the Graham-Schmidt process, how can we make orthogonal basis, 그렇죠? orthogonal basis V1, V2, VP, orthogonal basis. 그렇죠? That's going to be our goal. Then we can do so many kinds of things. 그렇죠? So how can we use this one? There are also so many kinds of application. 그렇죠? What was that? In lecture 9. So for example, lecture 9 어디 있더라? 그렇죠? lecture 9. We can find out, where's that? 그렇죠? If you have an orthogonal basis, you can easily find the operation of the y, 그렇죠? Onto the W subspace, or so on. So today we will use this kind of technique to derive the least square problem, least square solution, which is the approximated solution for your inconsistent system A equals C. We'll talk about this one later. So anyway, Graham-Schmidt process aims to find the orthogonal basis. 자, first of all, let's derive this one. First of all, let's suppose that V1 is equal to x1. V1 is equal to x1. Then, based on this one, let's just assume that substrate W1 spanned by V1 or x1 or x 이렇게 볼까요? 그냥 or x1 그렇죠? spanned by x1 because x1 and V1 is equal each other. Then V2 can be determined by x2 minus orthogonal projection of the V1 onto the W1 space. Something like orthogonal projection of x2 onto W1 space. 그렇죠? W1 is like this. 그렇죠? Like this. So this one is going to be x2 minus x2 inner product V1 over V1 inner product V1 times V1. That's it, V2. V3. So by using V1 and V2, we can determine by W2 subspace. 그렇죠? Spanned by V1 and V2. Then V3. When you have the x3, V3 is going to be x3 minus this one, which means like this one, it's going to be orthogonal projection of x3 onto W3, W2. 그렇죠? like this. So it means that V3 is equals to x3 minus orthogonal projection of the x3 onto the W2. Blah blah blah. Similarly, VP is going to be XP minus here, the XP minus projection of XP. XP 그쵸? XP onto WP minus 1. Where WP minus 1 it's going to be spent by V1, 2, V3, 뭐 blah 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 VP minus 1 그쵸? 됐을 때 그쵸? Then it's going to be V3. In other words, when you have the V1, 2, 3 VP, we finally achieve orthogonal basis. Orthogonal basis, which means like V1, V2, VP for substrate W. That's the Gram-Schmidt process. That's Gram-Schmidt process. That's it. So from now on, we just use this theorem, 그렇죠? Or this process to generate orthogonal basis for the arbitrary substrate W. This Gram-Schmidt process. V1 through the VP is orthogonal basis for the double substrate. In addition, span by V1 to K is equal to span by X1 to K. For 1 is equal to K to V. So like this, 그렇죠? As we discussed so far. We skip the proof since we can easily understand it from the previous example. 그렇죠? We can skip this one. 그렇죠? Skip the proof this one. 그렇죠? We can just use this theorem here and here. 자, this is also this is the Gram-Schmidt process. But in many cases, some problem definition required also normal basis, not instead of orthogonal basis. But we can easily derive the orthonormal basis from the orthogonal basis V1 to the VP. How? Just simply normalize or scaling all VK to have 1 as a sum. 그렇죠? 자, for example, previous example, construct the orthogonal basis V1 and V2 for the some substrate W. 그렇죠? Then also normal basis, let's say U1 or U2 can be derived like the normalizing V1 and V2 by length of this one, length of the V1 and length of the V2 respectively. So like this. 그렇죠? How can you do that? So given the x1 is like this, length of the V1 is going to be length square root of 3제곱 plus 6제곱. It's going to be like this, or 3 over 3 square root 5. So it's going to be 1 over square root of 5, 2 over square root of 5, 0. Similarly, x2 it's going to be 0, 0, 1, 0, 0, 1. That's the orthonormal basis. 그렇죠? It means that given any kinds of any substrate W and any kinds of basis, we can easily derive orthogonal basis by using a Gram-Schmidt process, and we can easily find the orthonormal basis by just normalize each vector independently like this. Right? And okay. So then now we can derive QR factorization. So in fact, QR factorization is a byproduct of the Gram-Schmidt process. So in this semester, we already discussed LU factorization, which is one of the factorization method that can factorize the original matrix A. So from now, we'll talk about the QR factorization, but I strongly suggest to you, please compare step by step LU factorization and QR factorization and compare each pros and cons between them. Anyway, QR factorization is just byproduct of the Gram-Schmidt process. Right, so first of all, let's talk about the high-level definition. I mean the just definition of the QR factorization. 자, let matrix A is an n by n matrix with linear independent column. linear independent column. It means that 여기다 그려볼까? Q matrix A consisting of m columns, m rows and n columns. 그쵸? Like this. And they are, the column vectors are linearly independent each other. The linearly independent column. Dependent columns. That's the assumption. Assumption. Then matrix A can be factorized as A is equal to QR. So first of all, if matrix A is not linear independent column, then matrix A maybe cannot factorize as A is equal to QR. Anyway, we need just assume A is equal to A has a linear independent column. A can be factorized matrix Q and R, where matrix Q is n by n matrix whose columns form a orthonormal basis or column space of matrix A. And R is a n by n upper triangle inverter matrix with positive entry in each diagonal. In other words, matrix A can be factorized by, let's say, Q and or Q times R, where Q consisting of m by n matrix, and each column vectors are also normal basis for column space of matrix A. 그쵸? And or whose size was n by n, which is the rectangle matrix, 그쵸? And upper triangle matrix like this one, and positive entry on each diagonal always. 그쵸? In this case, we call this is a QR factorization. 자, let's go back to the Gram-Schmidt process. 자, Gram-Schmidt process make a orthogonal basis for the just basis. 그죠? They are linear independent. 그죠? And span subspace W, which means like in QR factorization, this one column vector is going to be the basis for the linear independent column vector is going to be the basis for the column space. Then Q is going to be the orthogonal basis for the column space, which means like matrix Q, the column vectors matrix in matrix Q can be derived from column vectors of matrix A, which means like it's going to be Gram-Schmidt process. Then, or can be just found during Gram-Schmidt process. So this is a QR factorization. 자, first of all, before derive the QR factorization, let me just start from the proof of this theorem. But so here it's just enough to show how we can construct the Q and R in a way specified this theorem. 그죠? Here's how. 자, let's do that. So let's remember the QR factorization, and let's construct the matrix Q and matrix R. 자, first of all, in this definition, columns of matrix A form a basis for the column space matrix A. Why? Because they are linear independent, linear independent, and span column space. 그렇죠? So column space matrix A themselves form a basis, 그렇죠? basis다. So it means that let these columns be the set of the vector. 그렇죠? Then we can construct the also normal basis U1, U2, and UN for this subspace by using the Gram-Schmidt process that we discussed so far. 그렇죠? 그렇죠? 자, then using this basis, we can just construct Q by setting this orthogonal basis as a column vector of matrix Q. Then we can just found a matrix Q. So that's it. What about this? Construct of the matrix R. Construct matrix R. In Gram-Schmidt process, we just assume that K is equal to 1 to the n. Xk is in just like span of the x1, x2, and xk, which is equal to span of u1, u2, and uk. 그렇죠? Where? Here. 그렇죠? Just assume that. I just found that. 그렇죠? 얘는 알고 있었고. 그러면 therefore there exists the coefficient or constant r1k, r2k, or kk satisfying such that xk is going to be the, because xk is in span u1, u2, and uk, xk can be represented by linear combination of the u1, u2, and uk plus 1 un, but we already know all these terms it's going to be 0, 그렇죠? Because we also assume that this is in just like this subspace, this space, 그렇죠? From x u1 to the uk, yeah? Then should be exists like this one, 그렇죠? So we can always make rk is larger than or equals to 0. How? If rk is smaller than 0, multiply both rkk and uk by -1. 그렇죠? We can always make this one. I mean, we have to make this one to make a further process easier. Anyway, using this linear combination representation, we can just construct rk. I mean the coefficient vector. Coefficient vectors of this one, because rk is going to be r1k, r2k, rkk, and 0, 0, 0, 0 vector. So, or transpose, and transpose. So, in other words, similarly, we can just make r1, which is going to be, in this case, 써볼까요? Let's say some constant value r1, 1, and 0, and 0 transpose, or r2 is going to be r 1, 2, 그렇죠? r 2, 2, blah 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 0 transpose, like rk is going to be r 1, 1k, r 2k, blah blah r kk 0 transpose, like this. There exists vectors like this. Why? Because the xk can be represented by this linear combination of the span of the u1, u2, and uk. So it should be exist this vector r. That is xk is going to be the q times rk. Q times rk. Q times rk. Why? Because when we just assume that, I mean, 여기서 써볼까요? So 여기서 볼까? Q is just like this one, 그렇죠? Q is the linear combination of the U1. Q is just a matrix with U1, U2, and UN. So it means that here xk is going to be the Q times rk, because Q is it's going to like U1, 여기 보면은 U1, U2, UN times RK, which was like this, 그렇죠? Like this. So xk is equal to QRK, for k is from the 1 to the n. Then we can just set R, matrix R, consisting of the column vectors with R1, R2, and Rn, which is defined like this. 그렇죠? So in other words, matrix A consisting of the x1, x2, and xn can be represented by here, 그쵸? qr1, qr2, qrn, which is equal to qr. Where r is like that. 그쵸? r is like that. The fact that r is invertible, 그쵸? The fact that r is invertible follow easily from the fact that cones of matrix A are linearly independent. 그렇죠? linearly independent. 됐죠? So in other words, R is clearly upper bound and invertible because R was shaped like this. 그렇죠? 이 R을 다시 매트릭스로 만들어 보면 clearly upper triangle and invertible and triangle entry should be non-zero. 그렇죠? non-zero. Why? Because this is the R matrix. R is the n by n matrix. It means that it's a square matrix, so it just follow the IMT inverter matrix theorem. So it should be non-zero vector on diagonal term. Combining this with the fact that RK is larger than or equals 0, RKK must be positive. 그렇죠? Must be positive. So anyway, there exists the matrix Q and R that can that are coming from the matrix cell A. That is a QR factorization. Anyway, we will just use this theorem, 그렇죠? To factorize matrix A and B. Matrix A for the KR. 자, first of all, let's do that. 자, first of all, let's find the QR factorization of matrix A. Define like 1, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1. Matrix A consists of x1, x2, and x3. 그렇죠? Then, so, first of all, to find the Q, let's find the Q first. 그렇죠? Then, considering the R during the description process. First of all, 자, 해봅시다. Because they are linearly independent of each other. 그렇죠? We can easily do that. We can usually know that. Linearly independent. So, first of all, let's use Gram-Schmidt process. Schmidt process. 그렇죠? process. 자, let's do that. First of all, V1 is equal to x1. 그렇죠? And to consider the normalized vector, let's say u1. It's going to be the 1 over 2, 1 over 2, 1 over 2, 1 over 2. 그렇죠? Just normalize this vector. 그렇죠? So, it means that u1 was like v1 over length of the v2. Sorry, v1. 맞죠? So which means like. So from this computation, x1 was like 2u1. Why? Because this one is like s1 over length of the x1. So because length of the x1 was 2, so from here x1 is equal to 2u1. So which gives us R11 is equal to 2. Where R1 is defined like this. 그렇죠? 2, 0, 0. So this is just a byproduct of the R during the Gram-Schmidt process. But at the end of this lecture note, we will talk about the more, systemic way or more efficient way to find the matrix R. But from now on, as of here, let's discuss the how to derive this R during the Gram-Schmidt process. So next, V1 is going to be the V2 minus fraction of the V2 onto the W1 space, 그렇죠? W1 space, which is equal to like the x2 minus this one, 그렇죠? So x2 was like this from here to x2, and orthogonal fraction of the x2 onto the W1 is going to be like this, 그렇죠? Please try to derive yourself. And anyway, this is going to be the negative 3 over 4, 1 over 4, 1 over 4, 1 over 4, which was like the V2. Thus, the normalized vector U2. 자, U2, which is equal to V2 over length of V2. It's going to be like this. So you can just do that. And to find out x2, let's say this one. So from this one and this one, 그렇죠? x2 is going to be the v2 plus x2 inner product u1 inner product over u inner product u1 times u1. Then from here v2 from here, so v2 is going to be the length of the v2 times u2, 그렇죠? u2. Then x2 u1 over u1 in the product u1 times u1, 그렇죠? Like this. Surprisingly, we just represent x2 as a in terms of the u2 and u1. Then based on this one, we can just find out r11 and r12 and r22, 그렇죠? r12, r22, r22, 그렇죠? So because this is the definition of the r, 그렇죠? Definition of r. So anyway, here this is r2죠. 여기가 r2인데, so vector r2 is going to be 3 over 2, 그렇죠? 3 over 2, 3 over scale to 12, scale to 12 and 0. 그렇죠? Anyway, as I mentioned previously, we can find out more efficient way to find the matrix R, but here just describe how to derive each vector R1 and R2, so, like this. So similarly, we obtain V3 is equal to x3 minus orthogonal operation of x3 onto the R2, the substrate W2, which means like x3 minus this one. So please try to yourself. X3 is here. This one, it's going to be the 3 over 2. It's going to be 1인 것 같아요. 계산해보면은 this is U1, this is U2, derived from the previous slide. Then this one, finally, it's going to be, for example, V3. And it's normalized vector U3, which was like V3 normalized by V3, length of the V3. It's going to be here. This is U3. So, based on this one and this one, we can represent x3 in terms of u1, u2, and u3. Please try to yourself. And finally, your x3 can be represented by u1, u2, and u3. So our 3 is going to be the 1, 2 over scale to 12, 2 scale root of the 6 transpose. So in other words, we just fill matrix Q because it consists of U1, U2, and U3, which are result of the Gram-Schmidt process, and we can just build R from the R1, R2, and R3 like this. So R3, R and Q, RQ. So in other words, this matrix A can be factorized by Q and R. So Q and R. So this is the QR factorization. So because this is a recorded video, so I will just skip the question. But if you have any question, please let me know and TS know. So please send me an email via my email. Anyway, this is a QR factorization. So alternatively, finding the Q is much easier comparing to the R, 그렇죠? So if Q was already computed, or if Q can be just found by Gram-Schmidt process, then one can just compute R, and because of Q transpose A is equal to Q transpose QR, which is equal to I times R, because K consists also orthogonal also normal vector. So Q transpose Q is equal to the identity matrix. 그쵸? That we discussed the previous lecture note. So this is going to be R. So it's going to be R. 그쵸? So in other words, R. I mean our interest R. It's going to be the Q transpose A. So we can just find the Q by orthogonal Gram-Schmidt process. So R is going to be the Q transpose. The Q transpose and A, origin matrix A. Then it's going to be looks like this. Or so by the way, this thing would be plus here. This is R. This is R. So we can just found matrix R first by comparing the Gram-Schmidt process and field Q and just find out Q transpose A. 그죠? That's the correct factorization. 자, that's it. So this is lecture 10. This is lecture 10. So that's it. So from now on, let's move to the lecture 11. Least square solution. So this is the just application of the lecture 9, lecture 10. So from now on, we'll talk about least square solution. I mean, this is approximate solution by using some kinds of orthogonal projection. So let's do that. So if you just follow the what we've done so far, you can easily understand the least square solution. But if you're not, maybe it's going to be very, very difficult. So please, people, follow this one, recap or review. 그렇죠? yourself. 자, anyway, this is about chapter 6.5, least square problem. 자, let's do that. 자, first of all, least square solution problem want to solve like as follow. The inconsistent system A equals B that have no solution arrays of in question. Maybe most of application does not have any solution. I mean, most application is going to be the inconsistent system. But, however, when a solution is demanded and non-exist, the best one can do is to find out X that make AX as close as possible B, even though X is not equal to AX or B. I mean the AX not equal to B, even though AX is not equal to B. But we have to find the approximate solution that satisfy AX equals approximate to B. Think of AX equal AX as an approximation to B, but as close as possible. So in this case, general least square problem is to find out X that makes B minus AX. I mean the approximation error between B minus AX and B and AX as small as possible. 그렇죠? Which means like X is equal to approximated solution for X equals B. So why you have to know that? So to answer this question, please go back to the lecture 9. 그렇죠? 우리가 그랬던 거 있죠? 그렇죠? It is lecture 9. 그렇죠? page 4. 자, like this. 그렇죠? Even though we are interested in, let's say, vector B or C, which is outside of the column space, but we are interested in approximate solution. So which means maybe this vector, I mean the also operation of the C onto the W or column space is going to be the close factor on this W space or the column space. So that's the also operation of C onto W space. So this square solution is going to be exactly the same. So question is how to find out X that satisfies this one. So that's the today's topic. 자, 이해했죠? 그래서 한국말로 리캡을 해보면 오늘 얘기했던 것처럼 이렇게 orthogonal projection이 있는 경우, 그러니까 왜 배웠냐면 우리 얘기했던 것처럼 컬럼 스페이스 안에 못 들어온 벡터들은 사실 솔루션이 없어요, 이론적으로. 근데 이제 그거를 우리가 많은 태스크들에서는 이렇게 C가 밖에 있더라도 approximate 솔루션을 알고 싶거든요. approximate 솔루션이 가장 중요한 게 그냥 프로포레이션이 가장 가까운 점이니까 그 점을 만족하는 x가 아마 가장 에러가 작을 거예요. 저 그걸 그냥 쓸 거예요. 그래서 그 비슷한 시어럼이 우리가 여기서 배웠던 어디있죠? 패스 어퍼레이션이 사실 그걸 얘기하고 싶었던 거고요. 맞죠? 요걸 그대로 갖다 쓰는 게 이제 렉처 11에서의 리스큐어 솔루션, 리스큐어 프로블럼이에요. 그러니까 사실 똑같아요. 똑같은 얘기를 할 거야. 그래서 이걸 솔루션 관점에서 얘기를 할 거야. 알겠죠? 자, first of all, let me start with the definition. 방금 얘기했던 거예요. 자, 요 그림을 계속, 자, 요 그림. So please remember that the figure that I show you here. 자, so 리스큐어 솔루션. Here definition. If matrix A is n by n matrix and P is in a rem space, the riskier solution of the Ax equals B is an X prime in our space. From now on, we just represent this is the X hat, riskier also X hat, such that B minus AX hat is smaller or equals to P minus AX for whole X in our space. Whole X in our space. In other words, the errors between B and AX hat is the smallest, then X hat is going to be the riskier solution. 그렇죠? riskier solution. Or best this is the very similar to the best approximation theorem. 그렇죠? 우리 already discussed best approximated solution. theorem. Let's say theorem. 자, the most important aspect of a riskier problem is no matter what x we select, the vector x will necessarily be in the column space of matrix, column space of matrix A. Like, let's go back to lecture 9 here. 그렇죠? column space에 들어가면서 가장 C에, 가장 또는 B에, outside of this space에 가까운 애가 뭐냐는 얘기를 하고 있는 거죠. 그래서 we seek X, then make AX closest point in column space matrix A to the B. 그렇죠? So we already discussed this on the best of theorem. What was that? Just like this one. 그렇죠? This one. So this is our substrate W, which was the column space matrix A. 그렇죠? For any vector, let's say P in column space, let's say AX1, AX2, and AX hat. So here, this AX hat is the closest point from vector P to the W subspace or the column space, which means that here X hat is going to be riskier solution. Riskier solution. Then we already know when AX hat was like orthogonal projection of P onto column space. 그렇죠? column space A or subspace. Then X hat satisfying this one, it's going to be our solution of the general riskier solution, or just call riskier solution이다 라고 불릴 거야. 리스트 스퀘어 solution. Exercise is called riskier solution. So in other words, given A and B, apply the backsolver theorem to find to the column space of the matrix data 라는 거죠. 그죠? 똑같은 얘기요. So that's just called riskier solution. So anyway, let B hat is a projection of the B onto the column space of matrix A. 그쵸? B onto this one. Let's say this is the B hat. B hat. Because the B hat is in column space of matrix A. the equation ax equals b hat is consistent. I mean the ax equals b hat has a solution, always a solution, and there is a solution x hat in Rn such that ax hat is equal to b hat. Let's say this is the first equation. So anyway, since b hat is the closest point in closed matrix A to the B, vector x hat is a least square solution of the ax equals b if and only if x hat is satisfied 1. So in other words, solution for the b hat is equal to ax hat, where x hat defined in Rn space, which is equal to general least square solution. least square solution 이다라는 거죠. least square solution. So 거의 다 왔어요. 자, by the orthogonal decomposition theorem, orthogonal decomposition theorem, 그죠? Fraction b hat has the properties like p minus b hat is orthogonal to column space matrix A. I mean b minus ax hat. 그죠? b minus ax hat is orthogonal to the column space matrix A, like this one, 그렇죠? 여기가 항상 이렇게 orthogonal하다는 걸 알고 있죠. b minus ax hat이, 그렇죠? Is which means b minus ax hat is orthogonal to each column of matrix A, each column vector is matrix A. 자, and if J is any column of matrix A, like matrix A consisting of A1, A2, and AJ and AN, for example. AJ is any column vectors in matrix for matrix A. AJ inner product P minus AX hat is equal to 0. Why? Because they are orthogonal. Because they are orthogonal each other. 자, 거의 다 왔어요. So it means that based on this one, AJ transpose times B minus AX hat is equal to 1. Sorry, 0. So, since each J transpose is the row of the A transpose, like, 자, from the definition, A transpose is going to be like A1 transpose, A2 transpose, AN transpose. So we can represent this one, it's going to be A transpose times B minus AX hat is equal to 0 matrix, which means like A transpose B minus A transpose AX hat is equal to 0. Finally, A transpose AX hat is equal to A transpose B. A transpose B가 되겠죠? 그렇죠? 자, in other words, this calculation shows that each least-square solution of AX equals B satisfy the equation that A transpose AX hat is equal to A transpose B. 자, even though there is AX equals B doesn't have a solution, but approximate solution, I mean the least-square solution X hat should satisfy A transpose A X hat equal to A transpose B. So this matrix equation represents the system of equation called numerical equation of the AX equals B. Very, very important. Numerical equation of AX equals B. So in other words, numerical equation of AX equals B, where AX B doesn't have a solution, then solution of this, a solution of this numerical equation, it's going to be the X hat. This is going to be the least square solution이다. Then, even though we don't have, your system doesn't have any solution, then you can just find the approximate solution, X hat, from this numerical equation. That's it. So that's the very, very important theorem and properties. Then from now on, we talk about how to solve this one. Then how can you use this one and how can we effectively or efficiently solve this problem by using QR factorization. Right? So, thank you very much. We'll talk about this one in the next section, next chapter or next lecture. Thank you very much and see you next lecture. Before that, if you have a question on this or today's lecture, please let me know. Okay? Thank you very much. I'll see you.